Hey everyone, it's time for physics. Today, we treat light as a ray and learn how to model mirrors and lenses. And we're going to start with mirrors. Now, the easiest type of mirror to understand is what's called a plane mirror. That's just a flat mirror that you might find in your bathroom, and when you put an object on one side of it, that object will appear on the other side of it. We're going to call this the object. That's the real thing being reflected. And we're going to call this the image. Now this image, we can say a few things about it. We notice that this image is upright, meaning it's not flipped upside down. We also notice that this image for a plane mirror is going to be the same distance away that you are from the mirror. So this distance is equal to this distance. However, when the light comes in, the light is actually going to be reflected straight back. Or if light comes in at an angle, let's say you're trying to look at the new UGG boots that you bought, the light will come in at an angle and bounce off at the same angle that it came in at. Now all of the bouncing of the light rays are happening on this side of it. In order to see the image over here, what's constructed is what's called a virtual image. Meaning that the image over here, it's not a real image. It's not a real image, meaning that there's not an actual image being formed. We couldn't put a screen or something behind the mirror here and project this image onto it. So this is what's called a virtual image, and we'll talk more about that a little bit later on. So plane mirrors are easy to understand. Let's make it a little bit harder, and let's bend our mirrors. Let's bend our mirrors. There are two types of bent mirrors. These are the side views of these mirrors. And what I'm going to do is I'm going to draw a line right through the middle. That's called the principal ray axis. And again, we'll talk about that a little more later. It's just the central part of our mirror there. So these are two separate mirrors here. So if I have an object and it's on the inside of this curved mirror, this mirror is going to be what's called a concave mirror. Okay, this is the object. If I have an object and it's on the outside of the curvature surface, this is going to be what's called a convex mirror. Now the way that these types of mirrors handle light is going to be a little bit different. If I take a flashlight and I shine a bunch of light into this mirror, all the light rays are going to come in, and after they bounce off this mirror, they're all going to converge onto a single point. For a concave mirror, the light's going to come in, it's going to bounce off at an equal angle, just like a plane mirror, and they're all going to converge on this single point right here. And that point is what is called the focal point. The focal point. Okay? And the focal point just actually happens to be exactly half the distance of the center of curvature, or the radius of our circle. So you can think of these mirrors as just a chunk of a sphere taken out. But the focal length right here is going to be 1/2 the distance of the center of that circle. For a convex mirror, it's going to be a little bit different. The light is going to come in, but instead of all the light being converged to a single point on the other side, the light is actually going to be bounced off in all different directions. And none of this light actually converges. So if we're looking for an image, these light rays will have to be extended backwards. Let's do a couple of them here, to a single point. And the focal point of a convex mirror actually lies on the other side of it. So what we want to do, if we want to model what these mirrors do, what we can do is we can draw what's called a ray diagram. Okay, and they're going to be a little bit different for mirrors and lenses, but for mirrors, ray diagrams, they have two types of rays that you need to draw. So I'm going to list them here. So for a ray diagram, there are two rays that we need to follow. One is going to be parallel to the principal ray axis through the focal point, and the second one is going to be through the focal point and then after it bounces off the mirror, it's going to become parallel to the principal ray axis. So let's do an example here using these two rules. And when you're drawing these free body diagrams, it's important always to use a straight edge. So here's our principal ray axis. We're going to do an example of a concave lens. And let's just say the focal point is going to be 1, 2 away. That means the center of curvature is going to be another 2 away. We'll call that R. And let's just say our object is well beyond both of those points. Here's our object. So let's follow the two rules. First, we need to draw a ray parallel to the principal ray axis. That's what this line is, principal ray axis. So we're going to draw a line parallel to that, and it's going to come in and strike the mirror. After it strikes the mirror, then it's going to be reflected through the focal point in a straight line. So it's coming in here, and then it's going out there. The second one that we have to draw is through the focal point first, and then it's going to reflect parallel. So we're going to start from the tip of our object again, through the focal point. And this is why it's so important always to use a straight edge, so we get accurate results here. This ray is going to come in here, and it's going to be reflected parallel, because focal length to parallel. It's going to be reflected parallel, back off. And where these two rays cross each other, since we start at the point of the arrow has to be right there. So our object formed here, and our image actually formed right there. Now there's a couple things that we can say about this image. For one, we know that this image becomes inverted, and the second thing that we can say is that this image is going to be a real image. That means that we could take a little screen and we could put it right here in this area, and the image of our object would be formed on that screen. It would be a virtual image if we had to do something where we extended these reflected lines back, and the image would be formed on the other side of the mirror. Now this is just an example of one position for one type of mirror. In reality, in class I'm going to have you do 1, 2, 3, 4, 5 different ray diagrams for each of the possible positions that an object could be. Now mirrors have a couple different real-world applications beyond just your standard bathroom mirror. One of my favorite ones to talk about is the telescope. As discussed in earlier videos, a telescope is essentially just a light bucket. And at the end of this light bucket, we have a concave mirror. So here's our telescope. We're pointing it at some distant star out deep in space. That light from the star is going to come in to our telescope. We're going to get light from this star. And all of that light that it collects, by the way, the size of this mirror is much bigger than our eye, so it can collect more light. And all of this light is going to be reflected back to a single point, or the focal length of that mirror. So the light comes in from the distant star, and then it's all reflected to a single focal point, and then maybe you put some sort of plane mirror here to divert or redirect that light to an eyepiece out of the side of your telescope, where you can view that distant star with much more magnified light. Another place where you see convex mirrors are on blind spot mirrors on cars, or sometimes in buildings or on streets. They make it easier to see around corners. So now let's talk about lenses. So just like with mirrors, there are two types of lenses. Two types of lenses. The first type is what's called a convex lens. And what that does, let me draw my principal ray axes here. What the convex lens is going to do is light is going to come into the lens, And after it passes through the lens, that light is going to be redirected to that lens's focal length on the other side of the lens. So the image of that object over here will be formed on the other side at the focal length. And of course, double the focal length. Let's see, we have 1, 2, 3, 4, 5, 6. That's going to be the center of curvature of our lens. For a concave lens, the light is going to come in, but instead it's going to be diverted out. And if we follow those lines back, they will intersect with that lens's focal length right there on the other side. And of course, I guess you would call it a plane lens. Is just like your standard window that allows light to come in and go out the other side unaltered. So drawing a ray diagram for a lens is a little bit different than for a mirror, and it's going to require one more type of ray that we need to draw to make sure that we're on the right track. So I'll draw these requirements now for our rays. So the first two are actually going to be the same. We're going to have focal length to parallel and parallel to focal length. But the third one, it's pretty straightforward. It's just going to go straight through. And that's just going to be a good check for us to make sure that we're on the right track. So we're going to do another example here for a ray diagram using lenses. So I'm going to draw again my principal ray axis. I'm going to draw my lens here in the middle. We're going to be working with a convex lens, and we're going to go 1, 2 again for the focal length, and 2, 3, 4 for the center of curvature. But this time the focal length of this lens exists on both sides of the lens, and we have to draw it accordingly. So then we have 1, 2, we have the focal length over here, and then 2 more gives us the center of curvature on this side over here. So again, we'll draw our object on the left side. We're going to make our lens just a little bit taller here. Keep my object just a little big. So we have to go through the focal length, and then when it comes out the other side of the lens, so top of the arrow through the focal length, when it comes out the other side of the lens, it's going to be going parallel to our principal ray axis. The next one, we're going to go parallel. That's why I had to draw this a little bit taller. So from the tip of our arrow, it's going to go parallel to the principal ray, and then it's going to drop down through our focal length there. And if we did everything right, our third one should check off straight through the center. We're going to go tip the arrow through the center of our lens, and that should hopefully line up, which it does, with where the other 2 rays were. So again, this is where the tip of our arrow is. So we have an image formed on the other side. Again, we can say a couple things about this image. Here's the object. Here's the image over here. It is going to be inverted, and it is also going to be a real image. And we know it's a real image because we can put a screen over here, and the image of our object over here can be projected onto that screen. This is actually how projectors really work. So this would be like your wall that you can project that image onto. Not every image from a lens is going to be real though. And tomorrow or the next day when I ask you to do the other positions of the object, so 1, 2, 3, 4, 5, at R, in between R and F, at F, and in front of F, you'll find that there are some cases where this may be a virtual image instead. And of course we have an equation to relate the focal length of the lens, the distance of the object, and the distance of the image as well. And it goes like this. It's called a thin lens equation. It goes like this. It goes 1 over the focal length is equal to 1 over the distance from the lens to the object plus 1 over distance from the lens to the image. Now the equation itself isn't that hard to manipulate. What you do need though to understand are the rules of this equation. So each of these terms you have to decide based on the situation if it's going to be a positive or if it's going to be a negative value. Think about this as learning a new card game or learning something like the Settlers of Catan. You learn the rules and then you just have to play the game. Okay, so the first rule here has to do with focal length. So for a convex lens, it's going to be positive. The focal length will be positive. For a concave lens, the focal length will always be negative. Okay, that's the first rule, dealing with the focal length. The second rule is going to be dealing with the distance of the object. That's always just going to be positive. We're always going to call the distance of the object to be positive. It's going to be in front of the lens. It's always going to be positive. That one's the easy one. And the third rule deals with the image distance. Okay, if the image or the distance to the image is negative, that means, actually let's start with positive. If it's positive, that means you're going to get a real image, and if it's negative, that means you're going to get a virtual image. So again, this equation describes the relationship between focal length, distance to the object, and distance to the image. But let's talk about some applications of lenses, and let's talk eyeballs. So a normal eyeball has a convex lens in front of it to help focus the light to your optical nerve in the back of your eyeball. So a normal eyeball will look like this, and of course the optical nerve runs to your brain. And what this convex lens does, well, the light it focuses the light on your optical nerve right there in the back. However, some people have lenses in their eye, their eye lenses. So some people's lens in their eye, though, like say people who are nearsighted, well, the lens in their eyeball will actually focus the image somewhere within their eye, and the optical nerve will pick up a blurry image. So if you have glasses, the lens of the glasses needs to move that focal length of the incoming light back to the sweet spot near your optical nerve there. If you're farsighted, it's just the opposite. That means your eyeball will take the incoming light and focus it behind your eye, and your optical nerve here will pick up another blurry image. So the lens that you wear in front of that will need to take the light and refocus it closer in order to line it up with your optical nerve there.